Camera coordinate transformation. Camera coordinate transformation is the final stage before we rasterize and project it on the screen. We change the world coordinate into a camera coordinate. The most important axis of the camera is the depth axis, which is the z axis, and that is the lookat vector. Next axis is defined using the up vector, where I would place the up position of the camera. This stick in my hand shows the up is vertically up here. If I change the up vector direction to the right, you see the camera changing its direction and the up vector has changed. Similarly, the up vector can change in other direction. So moment I have defined the camera coordinate and the up vector, the third orthonormal vector automatically gets defined. I can change the lookat vector, keeping me in the center, and I can do a circular pan or dolly around me, where you can see how the landscape behind me change while I remain in the same object or the center of the camera. Now let us see in detail how do I transfer or how do I make the camera coordinates so that I could transfer from the world coordinate into the camera coordinate. Viewing transformations. Viewing in OpenGL has a multiple matrix stack transformation function. Right multiply the top of the stack. The two most important stacks are GL model view and GL projection. Points get multiplied by the model view matrix first and then the projection matrix. So model view, object moving to camera coordinates, and GL projection, that is from camera coordinates to the screen coordinates, which is projection into 2D plane, and GL viewport, that is screen to the device. So this is an example of a GL code of how you would set up the viewing. A 3D scene, notice the presence of the camera, the projection plane, and the world coordinate axis. The world coordinate axis is shown below the chair. Here, these are the three. This is the world coordinate. And here what you see is the camera. And this is the projected screen which the camera is capturing of the world. The viewing transformation defined how to acquire the image on the projection plane. So viewing transformation, create a camera center view. We choose the camera is at the origin. Camera is looking along the negative z-axis, and camera's up is aligned with the y-axis. It need not be aligned with the y-axis, but generally we take the camera's axis to be aligned, the up axis to be aligned with the y-axis of the world. Two basic steps. Align the two coordinates frames by rotation, creating camera coordinate space. Specify a point where the camera is located in the world space, the eye point. We will call this as the eye point. Here the eye point is shown here by the red dot, which is showing the camera location. So we need to specify in the world coordinate where is the camera located, or we should have the coordinates of the camera or the eye point in the world coordinate system. Specify a point in the world that we wish to become the center of the view, the lookout point. We assume this green point as the lookout point. This is the point where the camera is looking at, and this would be the center of the viewing window that we will be seeing. Specify a vector in the world space that we wish to point up to the camera image as the up vector. That is, we choose an up vector. Up vector could be in the world coordinate, which is denoted by this vector, yellow vector here in this image. Now this is intuitive to the camera movements. We will see that some effects are described by changing the up vector of an image to create emotions or variations. We will see a portion of an image from Charlie Chaplin where how beautifully he has modified or shot the scene by changing the up vector of the camera to make it look like the boat on which they are traveling is swaying. So here I have got the world coordinate, and in the world coordinate I define the eye point or the camera point. Once I have the eye point, I could describe it by a vector called I, which could be represented in the world coordinate by Ix, Iy, and Iz. Then I would describe or place the look-at point in my world. So the look-at point is described by its three coordinates: look at x, look at y, and look at z. And this defines the look-at point or the center of my scene of my camera. So let me join the camera point to the look-at point, and this vector we will call it as the depth vector or equal to L vector, which is nothing else but look-at coordinate minus the eye coordinate. In the world axis, we define a vector up, where at look-at point, I defined an up vector which is equal to up x, up y, and up z at the look-at point. So let us construct the viewing transformation by creating a vector from the eye point to look-at point. So which we see is equal to Lx, Ly, Lz, which is equal to look at x minus look at y, look at x minus ix, look at y minus iy, and look at z minus iz. When we get Lx, Ly, Lz, we can normalize this vector by taking the modulus root of the modulus square at the denominator so that we get a normalized L vector. This is my first coordinate of the camera, and we need to, since we have taken the negative z-axis as my L vector, so we need to write my z coordinate or zi is equal to minus L. So what we see is that we have the up vector which is defined here, but this up vector and the look at vector are not perpendicular to each other. But what we know is that the y-axis exists on this plane, which is formed by the up vector and the camera or the look at vector. So since these two since the y-axis is on this plane, the x-axis is certainly perpendicular to this plane. If x-axis is perpendicular to this plane, taking a cross product between look at vector and up vector will provide us the direction to the x coordinate. So here I have got r, which is equal to L cross up. So we construct another important vector from the cross product of the look at vector. This vector, when normalized, should align with 1, 0, 0 transpose, which is equal to 1, 0, 0, which is equal to r by rx square plus ry square plus rz square. That is normalization of the vector r. So here I get my second coordinate, the xi coordinate, which is defined as r cap, which is xi cap. So now when I have the depth axis, which is minus L, and the x-axis, which is equal to r, I could then take a cross product between r and L to obtain my u vector or the y vector in the camera coordinate system. So this u vector is equal to r cross L, which can be shown as given here u upon root of modulus of u, which is equal to ux square plus uy square plus uz square. My y prime of I is equal to u.
Let's look a bit more in depth at how this box in space actually gets positioned and defined internally. First, we define our camera object as looking down the world's negative z-axis and oriented so that the top of the camera is facing along the plus y-axis. The camera starts at the origin, just like other objects. The first step is to move the camera to where we want to make an image from. We also tilt and orient the camera as desired. This is similar to how we've been orienting objects all along. We define some sort of rotation and translation to get the camera into place. We ignore scale, we're just trying to set up the camera in space. Giving the camera a position is simple enough. To compute the rotation needed to orient our camera, we use what's called a look-at system. This is pretty much what it sounds like. You define a target location for what direction you want the camera to look. This defines the negative z-axis for the camera's frame of reference, in other words, how it's pointing in the world. So here I have a real live camera. It even works. And with my z-axis here, that tells me which way it's pointing, but unfortunately it doesn't tell me which way is up. It still has this 1 degree of freedom. So what we do is we also define an up vector of some sort. This vector gives us some guidance as to which way to orient the top of the camera. Typically in 3JS we'll pass in a vector such as 0, 1, 0, the plus y-axis, as the up vector. Given our view vector and this up vector, we'd like to form a matrix that defines a whole frame of reference for our camera. We know where we want the z-axis to look along, but we want to know where the camera's y and x-axis end up. By specifying a general up direction, we do this. For example, say we have a camera pointing in some direction, looking along its negative z-axis. If we give an up direction, we can find the direction pointing to the right of the camera, which is the x-axis, by taking the cross product of this z-axis and our up vector. Now we have two axes locked down, camera z and camera x. We can find the true up direction, the camera's y-axis, by then taking the cross product of the x and z axes. Remember that the cross product of two vectors will give us a vector that's perpendicular to both of them. This may all sound a bit odd and like a lot of work, but is extremely common. It's probably the place where I use the cross product the most. The whole point here is that, given a view direction and an up vector as a hint, we can get a frame of reference for the camera. We'll often use the world's plus y-axis as our up vector hint, but it all depends. Say we're a hawk soaring over some terrain. We're looking straight down, which would be looking down the y-axis of our world. If we use the world's y-axis as our hint, it doesn't make much sense. We define the negative z-axis the camera is looking along and the y-axis for the camera's up direction as vectors in exactly opposite directions. This is not very useful. In this case, our up vector is more like the direction pointing out of the top of our hawk's head, the direction it's flying. Now that the up vector is not parallel to the look-at direction, we can form a good frame of reference for the hawk.
So viewing transformation V must convert from a world to a camera coordinate system as shown here. I have two orthonormal coordinate systems, that is, one is the world coordinate system and the other is the camera coordinate system. But we know that both these coordinate systems are not concentric. Now to make them concentric, I need to translate the world coordinate to the camera coordinate. I can easily do this by subtracting the coordinates of the camera from the world coordinate, which will automatically coincide both the origins together. When I manage to coincide the origin, I could easily do a dot product between the camera coordinates and the world coordinates, and of course I subtract the camera with the XYZ coordinate, that is the camera's position, to get my final camera coordinate x prime, y prime, z prime. This is more clearly shown here as a matrix. We have seen how to transform two orthonormal coordinate system, concentric orthonormal coordinate system. Here you have a translational term which makes both the coordinates concentric, and you have this portion of the matrix is nothing else but transformation from one orthonormal coordinate to another orthonormal coordinate which are concentric. So when we have this, from this RU minus L I coordinate, I can easily generate the camera coordinates, which is equal to xi, yi, and zi. So here in this image, you see that I have put a world coordinate in the corner, and which I need to transform it to the camera or the I coordinates as shown here. And from that, we need to transform this whole world from the perspective of a camera so that we can do the relevant transformation. This is a contraption which Charlie Chaplin might have used, where I have a camera which is fixed on a pendulum. By rotating the pendulum, I rotate the camera to and fro from left to right, and in the process I can generate the effect of a rocking boat.
Hi, this is Ben Modell. I'm a silent film historian and accompanist, and we're looking at a particular shot from The Immigrant, starring Charlie Chaplin, that's always intrigued me. We know this was taken on deck of a boat that wasn't really rocking back and forth that much, and that to create this effect, the camera was mounted on some sort of a pivot, giving it that tilting motion. But if the camera is tilting and the boat isn't really rocking, how is it that Charlie is sliding back and forth and at the exact moment that the camera is tilting? Well, this was a brilliant effect that Chaplin figured out. So what I did is I slowed it down to real-time speed and straightened out the image. Let's take a look how Chaplin achieved the image. So this is what it looked like for Charlie, basically. The boat, as you can see from the horizon, isn't really rocking that much. And we can see that Charlie is translating his upper torso. In other words, he's sliding just the top half of his torso to one side as a sort of lean. And in a moment, now watch his foot. He's going heel toe, heel toe, heel toe at the exact same time that he's translating his chest. So he's giving the impression of leaning or being pulled at the same time he's doing this slide. In real-time speed, it's pretty obvious what he's doing. But when it's sped up and coordinated with the tilting of the camera, you don't see that wiggle, you just see his whole body slide. And you know that the tilt of the camera was coordinated, so somebody must have cued Charlie. Or he was just watching carefully the camera. So the camera would tilt, and he missed one there. There's another one he catches. There's another one. See there? And you can really see the foot there, if you really watch it. And Chaplin knew that you wouldn't really be watching his foot, you'd be watching his whole body, especially if the whole thing was sped up. What's interesting here is, just at the moment of the belch, the rocking of the camera stops. Right here, just to get the belch out. Then it resumes. Brilliant.
The camera sees a small section of the world through a limited screen. This depends on the pointing vector or the look-at vector. As the look-at vector changes direction and the elevation changes, the different portion of the world is revealed. This is a picture taken of IIIT Allahabad from a drone. As the drone lands, we get a different perception of the world.